Hello everyone, welcome to topic 8.5, acid-base titrations. By the end of this, you should be able to explain the results from the titration of mono or polyprotic acid or base solutions in relation to the properties of the solution and its components. Okay. So acid-base reactions can be carried out under controlled conditions called a titration. Titrations are qualitative ways to analyze acid-base reactions. Typically, a known concentration of a base is added to an unknown concentration of an acid or vice versa. The volume of both solutions is measured and used to calculate the unknown concentration. The solution with a known concentration is known as the analyte, and the substance, or titrant, the solution that we know is the titrant. The solution that you are studying or analyzing is called the analyte because you are analyzing it. In the diagram to the right, a base with a known concentration is quantitatively added to the Erlenmeyer flask. The flask contains a monoprotic acid with a known concentration, but with an unknown concentration but a known volume of 25 milliliters. The volume of the base titrant is found by volume reading the difference, because remember you have to take the difference when we read a burette. For example, the volume transferred to the flask is 26.27 milliliters. If we know the concentration of the base to be 0.1010 molar sodium hydroxide, we can then calculate the concentration of the acid in the burette. In a typical titration, indicators are used to help identify the point where the moles of acid and the moles of base are equal. This is known as the equivalence point, which is the point at which an indicator changes color is known as the end point of the titration, because you can't go past that color change. Indicators should be chosen so that the pH at the end point and the pH at the equivalence point, so when the color switches, the end point, and the moles of acid and base are equal, are very close to each other. So at the equivalence point, the moles of acid equal the moles of base, which means that the reaction goes to completion and that there are no excess reactants or products. And you can then calculate the previously mentioned problem using this example. So a titration curve can be constructed by plotting the pH against volume of titrant added. The titration curve is useful for summarizing results from a titration. The shape of a titration curve differs based on the identity of the titrant and the analyte. Factors to consider are the strength of the acid and the base, the number of hydrogen ions and hydroxide ions that will dissociate, and the concentration of both the acid and the base. If we look at the titration of a strong acid with a strong base, we see this curve for HCl being titrated with sodium hydroxide, hydrochloric acid being titrated with sodium hydroxide. When a strong acid and a strong base react, the equivalence point we see is at pH 7. This is the point when we have equal moles of the strong acid and strong base. When looking at the graph, the inflection point, or the steepest point here, corresponds to the equivalence point, so right at this spot. The volume of the sodium hydroxide NaOH needed to reach the pH of 7 can then be used to calculate the unknown molarity of the hydrochloric acid solution using the equation here. This works for monoprotic acids, or where the base to acid ratio is a 1-to-1 ratio. Okay, because it's only showing that here. You could also adjust it if you are able to determine the concentration of the hydroxide ion itself. Okay, but this is specifically for monoprotic acids. We'll see polyprotic later. The titration of a weak acid with a strong base gives the curve seen to the left. This example of titration curve is a weak acid titrated with a strong base. In this example, the weak acid is potassium hydrogen phthalate, abbreviated to KHP, which is being titrated with a strong base, sodium hydroxide. The general shape of the curve is similar to the strong acid, strong base curve, but there are a few differences. We are going to determine the steepest part, or the inflection point, of our curve to determine the equivalence volume when moles of acid are equal to moles of base, which is right here. So this would be it. Right. When a strong base is added to a weak acid, the pH at the equivalence point we see is above 7, because as the weak acid is neutralized, the conjugate base is formed, causing the solution to be basic. This happens as the reaction works to reestablish equilibrium. We can also use this titration curve to determine the pKa, or negative log of Ka, of the weak acid. The pKa is equal to the pH at the half equivalence point that we see here. Right? So this is our pKa. Because half of the initial concentration of the acid will have been neutralized and have formed the conjugate base. So when we use the Henderson-Hasselbalch equation, the ratio of acid to conjugate base is 1, so the end of that equation drops off and you're left with pH equals pKa. The last thing to note is that with this graph, there's a section between 5 and 25 milliliters of base added where the pH of the solution doesn't change much, right? We see that here, right? This is a very gradual slope, especially compared to the titration of a strong acid with a strong base. This is called a buffering region. This will be discussed further in a subsequent unit when we get to buffers. Also, titrations involving polyprotic acids. We see on this titration curve a diprotic acid like sulfurous acid being titrated with a strong base. We recognize it as diprotic because there are 2 inflection points, so this one and this one. And remember, those are the regions of the curve where the slope appears to be at its steepest. These 2 points correspond with the equivalence point for each of the protons being donated, because it's H2SO3. We can determine the pKa for each of these protons being donated by using the half equivalence point for each one, as we had done in the weak acid strong base titration above. Because there are multiple protons that are reacting, the 2 protons will be donated sequentially instead of both at the same time. This is demonstrated through the diprotic acid having 2 different pKa values. Remember, that is around the region or how well it donates, so that first one will have a much lower pKa value, so it'll donate first. The second one, having a much higher pKa value, will donate second. The first proton is given pKa1 and the second pKa2. Graphically, pKa1 is pH at the half equivalence point, first half equivalence point, and pKa2 is the second. The concept of determining the concentration of each species present at any point in a polyprotic titration is not assessed on the AP exam, so don't worry about that math. Okay, so for our first I do, given the strong acid, strong base titration curve shown, estimate the equivalence point and determine the concentration of the hydrochloric acid if you're titrating 20 milliliters of hydrochloric acid with 0.121 molar sodium hydroxide solution. So our general equation, we should always write that out, is HCl plus NaOH is going to yield, and it is a unidirectional arrow because this reaction goes to completion because they are a strong acid and a strong base. Oops. So our equivalence point, we see this is our equivalence point, and this is about 20 milliliters. So our equivalence point is at about, oh, not 20, 25 milliliters. My apologies. Okay. So we know the amount of base added, we know its concentration, and we know the balanced equation, so we can convert it to moles of the acid and then calculate the concentration. So we have 25 milliliters or 1,000 milliliters to 1 liter. 1 liter is 0.121 molar or moles of sodium hydroxide. And then we have a 1 mole of sodium hydroxide to 1 mole of hydrochloric acid. Okay, when we solve that math, we end up with 0.00325 moles. We are allowed 2 sig figs, so I'm going to underline that. To find the molarity, we would divide by the volume of the acid we started with, and I'm going to convert that to liters in my head by dividing by 1,000. And when we solve this or run this math in our calculators, we get 0.15 molar hydrochloric acid. So that is the concentration of the strong acid that is our analyte. Okay, now for our we do. The graph below shows the titration of oxalic acid with sodium hydroxide. Label the equivalence point and estimate the pH at the equivalence point and the pKa of oxalic acid. Okay, well, our equivalence point is about the steepest, which I would say is about right here. Okay, and then that is a pH of about 8.7. I'm going to just roll with that. And then the pKa, you could say 8.5. I'm not using a ruler, but there we go. The pKa is going to be from the pH at the half equivalence point. I see 30 is about my volume added, so I'm going to go to 15, and that's my half equivalence point. I'm going to draw over, and apparently I can't draw a straight line. And so my pKa, I'm going to say is about 2.9, because that's my half equivalence point, because halfway to the equivalence point is where I find my pKa, and then this is my pH at the equivalence point. Okay, so that concludes the notes. Please work on the you-dos. Make sure you check your work, and thank you for tuning in.